Hello all, I'm Kos Ferles and I'm going to present our work titled Verifying Correct Usage of Context-Free API Protocols. This is a joint work with John Stephens and Isil Dillig. Let me first give you a bit of a motivation for the problem we address in this paper. It is well known that application developers rely heavily on third-party APIs. These APIs, no matter how well engineered, always require developers to follow a certain protocol when they use them. Now, when developers misuse these APIs, this can lead to severe bugs and security vulnerabilities. And of course, this happens quite a lot. For instance, a recent empirical study showed that the big percentage of crypto-related vulnerabilities is due to an API misuse. Because of this, there has been an extensive body of work, also known as type state analysis, that tries to statically prove that an application uses an API correctly. However, type state analysis accepts API protocols only as finite state machines and therefore cannot handle real-world APIs with context-free API protocols. As an example of an API with such a protocol, consider Java's reentrant lock class that requires client applications to properly match the number of calls to methods lock and unlock. Since we have to keep track of the number of calls to specific methods, it is apparent that this protocol cannot be expressed as a regular automaton. And of course, similar protocols are also present in several other real-world APIs. For example, these languages here present a simplified version of the API protocols for Android's Canvas and Wake lock classes. And as I mentioned earlier, misusing these APIs can be quite detrimental for a client application, since it can lead to all sorts of troubles, from application crashes to resource leaks and deadlocks. Therefore, it is quite important to ensure that client applications use these APIs correctly. Furthermore, in practice, these protocols can get quite involved and they are not limited to just tracking the number of calls between a couple of methods. For example, these two context-free grammars describe the API protocols for Android's Wi-Fi lock class and for JSON generator, a class from generic JSON library. Now, let me show you how a typical tool in this area looks like. As I mentioned earlier, type state analysis tools accept an API protocol as a regular automaton. For example, this automaton here describes the API protocol for a socket class. Typically, a type state analyzer takes this protocol and a client application as inputs, and they either prove that the client application uses the API correctly or indicate the existence of an API misuse. In this work, we propose CFP Checker, a verifier that extends prior work since it can also handle context-free API protocols. Specifically, CFP Checker accepts API protocols as context-free grammars instead of regular automata. Let's now see how a user of CFP Checker can specify a context-free API protocol. For this, let's consider Java's reentrant lock API, which is the protocol I'm going to use throughout the presentation to demonstrate how our technique works. One important thing to note here is that this object L in this language is implicitly universally quantified. That is, if we want to prove our application does indeed conform to this protocol, we need to do that for every lock object generated by the input application. One key challenge that arises from this fact is that modern programming languages allow programmers to introduce aliases for heap objects. Therefore, a single object in the program's memory can have multiple names in the program's representation. To address this, CFP Checker specification language allow users to use special symbols we call wildcards, which are denoted by this $sign followed by a numeric value. For example, $1 here for this API protocol is going to match any lock object generated by the input application. So a user of our tool is going to provide the equivalent of this language as a context-free grammar that looks like this. And the formal property we're going to assume for this grammar is that its language represents all valid sequence of API calls with these special wildcards as arguments. And now that we saw how a user can specify an API protocol for CFP Checker, let's zoom in and see how CFP Checker is structured internally. The first step of CFP Checker is an instrumentation phase that deals with all the challenges that arise from these special wildcards present in the input API protocol. Then, in its core, CFP Checker is a counterexample guided abstraction refinement loop that performs the following steps. First, it abstracts the program's API usage with a context-free grammar. Then it checks whether the language of the program's abstraction is a subset of the language generated by the input API protocol. If this is indeed the case, then CFP checker terminates with a proof of correctness that the input program conforms to the API protocol. If that doesn't hold, that means that there exists a word W that belongs in the program's context-free grammar, but not in the protocols. In this case, CFP checker will map this word to an execution path and check whether this path is feasible. If the path is indeed feasible, then CFP checker will return this execution path to the user as a witness of an API misuse. If the path is infeasible, that means that this counterexample is spurious and thus CFP checker will refine its abstraction in such a way that ensures that this execution path is no longer a part of it. CFP checker will continue performing the same steps until one of the two termination conditions I mentioned earlier is met. In what follows, I'm going to describe each of these components in more detail, with the exception of the component that checks inclusion between two context-free languages. For the purposes of this work, we assume this is to be an oracle, and from a practical point of view, we use a technique proposed in a fairly recent UPSLA paper. Before I dive into the technical details, allow me to introduce the motivating example I will use to describe all these components. This example consists of three methods, namely foo, acquire, and release, each of which take an object of type log as an argument. Method foo is a recursive method that calls methods acquire and release before and after its recursive call site, and method acquire simply calls method lock on its argument, and respective method release calls method unlock. And as I mentioned earlier, we're going to check whether this program conforms to the reentrant lock API protocol I presented earlier in this talk. Now, if you study this program a bit more closely, you will see that it does conform to this protocol, since method foo passes exactly the same object to both methods acquire and release. And with the motivating example in place, let's now see how CFP checker is internally implemented. First, I'm going to present the instrumentation phase that deals with the wildcards in the specification. Intuitively, this instrumentation is going to deal with the issue that the input API protocol uses these special wildcards as arguments to the API methods, whereas the input program uses plain variables. So basically, the instrumentation is going to somehow replace program variables in P with these wildcards in P prime. And it's going to do it in such a way that P will conform to the API protocol if P prime does. Let's now see how the instrumentation works on our motivating example. First, I'm going to describe the instrumentation operationally and then give you an intuition of why it does actually work. So the instrumentation is going to perform the following steps. First, it introduces a global field for every wildcard that appears in the protocol and initializes it to a non-deterministic value. Then it replaces all program variables of every API call with this global field. So for example, L1.log in acquire will be transformed to $1.log. Finally, it guards all these transform API calls with an if statement that checks whether the original program variable equals to the wildcard. For instance, in our motivating example, it will introduce an if statement in method release that checks whether L2 equals to the wildcard. So what this transformation does is that it first picks a random object and then only considers the API calls that involve this specific random object. Essentially, the transform program checks whether the original program conforms to the protocol one object at a time. And since we don't restrict how these random objects are being initialized, it is safe to say that if the transform program conforms to the protocol, then so does the original. And that is going to conclude the technical description of the instrumentation phase. Next, I'm going to describe a single iteration of our abstraction refinement loop. Specifically, I will first show how our technique abstracts the inputs program API usage using a context-free grammar. Then I will show how we map a counterexample to an execution path and check for its feasibility. And finally, I will present our refinement algorithm that eliminates spurious counterexample from the program's abstraction. To present these components, we will use what is called a control flow automaton, or CFA, a fairly standard structure in program verification. Specifically, for every method, we're going to create an automaton that looks like this one, whose states are program location and its edges are labeled with program statements. Now, the program abstraction component is going to take the CFAs of every method and it's going to generate a context-free grammar that over-approximates the API usage of the program. Specifically, given a CFA for a method, it will do the following. First, it will introduce a NOR terminal for the method itself and one non-terminal for every CFA state. Then it will introduce a production for every CFA edge that captures the control flow dependency between these two states. Furthermore, if an edge involves an API call, the abstraction will contain a similar production that also emits a terminal to indicate the API usage. Next, for every exit node, meaning a node without successors, it will introduce an epsilon transition. Finally, if an edge contains a call to another method, the abstraction will contain a similar production as before that captures the intra-procedural control flow, but it will also use the callee method's non-terminal to capture the inter-procedural control flow. Now, if we put everything together, we're going to end up with a context-free grammar that looks like this. The important property we need to know here is that every possible sequence of API calls from the input program corresponds to a word in this grammar. The next step of our refinement loop is to ask our oracle whether the language of this context-free grammar is a subset of the API protocol. Now, if you study these grammars a bit more closely, you will eventually see that this doesn't hold. Specifically, this word right here is a counterexample because it belongs to the grammar on the left, but does not belong in the grammar on the right. As I mentioned earlier, CFP checker will now try to map this word to an execution path and check whether this path is feasible or not. In order to map this word to an execution path, CFP checker first obtains a parse tree for this word from the program's context-free grammar. After obtaining such a tree, it is trivial to map it to an execution path since there is a one-to-one mapping between CFA states and non-terminals. For example, this part of the parse tree that refers to method acquire is going to be mapped to this specific path. By traversing the rest of the tree, we're going to end up with an execution path that looks like this. Here, these dotted lines represent call edges and their respective return edges. Next, as it is standard in program verification, we're going to use an SMT solver to check the path's feasibility. If you observe this path, you will soon find out that it is actually infeasible because of these two contradictory assumed statements. Recall that method foo passes exactly the same object to both methods acquire and release. Now, in order to eliminate this spurious counterexample, we're going to use a standard trick in program verification, which is to employ Craig's interpolation in order to refine our abstraction. You don't need to be familiar with the specifics of Craig interpolation for the purposes of this talk. The only thing you need to know is that it's going to produce a mapping from program locations to logical predicates. And if our abstraction starts tracking these predicates to the corresponding locations, this will guarantee that this spurious counterexample will be eliminated. For example, for this specific execution path, we're going to get this mapping. As you can see, the interpolants dictate our abstraction to track whether the argument of every method is equal to the wildcard field or not, which, if you recall, it's the actual reason of why this counterexample is infeasible. So CFP checker is going to use this mapping in order to create a new context-free grammar that does not contain this spurious counterexample anymore. The first step in this process is to start tracking this predicate in our program representation. To do so, we're going to use what we call a predicated control flow automaton, or PCFA, which essentially augments CFA states by annotating their states with predicates returned by the interpolation procedure. For example, given this CFA for method acquire and these predicates, we will end up with a PCFA that looks like the following. The things to note here is that a single program location can now have multiple states in the PCFA because for each interpolant, we're going to track the interpolant itself and its negation. Also, we only keep the edges whose semantics are consistent with the predicates in both ends. So for example, here, we're only going to have an edge between states alpha 1 and alpha 3 prime, and not between alpha 1 and alpha 3. Now, in a similar way as before, we're going to generate the following context-free grammar given this new PCFA. Here, the top part of this context-free grammar is going to summarize all the execution paths where the argument of acquire does equal to the wildcard, and the bottom part, all the execution paths where this fact doesn't hold. And as you can see, it's only the top part of this context-free grammar is going to emit a terminal to indicate an API usage. Now, in a similar way as before, if we put everything together from every PCFA, we're going to end up with the following new context-free abstraction. The important property here is that the word that generated this curious counterexample is no longer a part of this abstraction. After this, CFP checker is going to perform another refinement iteration before proving that the program does indeed conform to the API protocol. And that concludes the technical description of CFP checker. Let me now move on how we implemented and evaluated CFP checker. CFP checker is built on top of the Suite bytecode framework and leverages two SMT solvers, Z3 for satisfiability queries and SMT interpol for interpolants. As I mentioned earlier, we use these techniques from this fairly recent UPSLA paper for checking inclusion between two context-free grammars. Finally, you can access the tool's repository by scanning this QR code. To evaluate CFP checker, we collected clients of these 5 Java APIs from 10 popular open source applications. And in total, we considered 12 unique pairs of API clients. The main takeaway of our evaluation is that CFP checker can effectively find bugs and prove correct usage of these APIs. Specifically, CFP checker initially found 3 bugs in these clients, and after fixing those bugs, it was able to verify all 12 clients. And the average running time across all these experiments is a bit less than 10 minutes, with the median time being around a single minute. To conclude, I just presented CFP checker, a tool for verifying the correct usage of context-free API protocols. Our technique uses a novel abstraction to over-approximate the API usage of the input program and proposes a new refinement algorithm that eliminates spurious counterexample from its context-free abstraction. Thank you all for watching, and I'm looking forward to seeing you during POPL.